transforming functions. Last time we talked about the three types of transformations that could happen to a function: dilations, translations, and reflections. And we also talked about parent functions. So now we're going to bring it kind of more into a general form. So this applies to all of those parent functions, but we're going to leave it in general f of x form for right now. All right, so now that we know there are transformations, how do we actually transform a function? Well, there's three ways to do it. The first way is by multiplying on the outside, which is represented with this a value. Okay, so an outside multiplication. You could also have an inside addition or subtraction, which is represented by h. And you could have an outside addition or subtraction represented by k. Now this form should look a little familiar. It should look like vertex form of a quadratic. It has the same variables, the a, the h, and the k. The only difference is that this is just for a generic function f of x rather than that x squared function for a quadratic. So instead of f of x minus h, if it said x minus h squared, that would make it a quadratic, and it would be in vertex form. But again, this will work for any of those parent functions we talked about before. Alright, so what do each of these pieces do? Well, the red piece, the a value, multiplying a number to the function, to the outside of the function, this does dilations and reflections. So the a value does two things here. It does two of the three possible transformations. The dilations, which change the shape of the graph, skinnier, fatter, and reflections, which change the positioning, if it reflects over a line or not. Okay, the inside addition or subtraction. Inside addition or subtraction represented by this minus h. This does horizontal translations. And finally, the adding plus k at the end on the outside of the function. So again, notice that h is inside the parentheses, inside with the x, and the k is outside of the parentheses, away from the x. This does vertical translations. So again, three transformations: dilations, reflections, and translations. And then kind of the translation being the umbrella term. You could have a horizontal translation or a vertical translation. Alright, so let's get into specifics for each one of these. Horizontal translations, again, these are adding or subtracting numbers inside of the function with the x value. There's two scenarios. You could have f of x minus h, so you're subtracting from the x value, or you could be adding to the x value. If you have a minus h, that's going to shift your graph h units to the right. So f of x minus h is going to shift h units to the right. Now, what does it shift? Well, it shifts every single point. So when we talk about parent functions, we talk about main points. And most of the time, those are the vertexes or the intercepts. So each of those points are going to move h units to the right if it's a minus h. If it's a plus h, your graph is going to shift h units to the right, or to the left. Now this one's always the one that's kind of opposite of what you think. Minus, usually on a minus on a graph, you're moving to the left, but in a translation, you're moving right. Okay, and usually plus, if you're thinking positive values on a graph, you're thinking to the right. That's where the positive x-axis is. But in translations, it's the opposite. It's moving it to the left. Alright, so same thing with the vertical translations. Whether you're adding or subtracting k in a vertical translation, that depends if it moves up or down. So if you're doing f of x plus k, so you're adding a number to the end of the function, that's going to shift your graph up k units. And then, as you could probably guess, subtracting k at the end of the function will shift your graph down k units. So this one's kind of the more intuitive one. Plus, on a graph, positive y-axis is up, so you shift up. Negative y-axis is down, so you shift down for minus. So those are straightforward. Now again, you can tie that back to vertex form. Vertex form is h comma k, but the h value is always the opposite of what we see, and then the k value is what you see. All right, and then lastly, the dilations and reflections. So these are two separate transformations, but they both rely on the a value. Okay. So the a values you're multiplying in front of the f of x. Okay. There's three scenarios. If the absolute value of your a value is greater than 1, so ignoring any positive or negative part of the a value, if it's the number itself for a is greater than 1, then you're going to have a vertical stretch. So that's a dilation. A stretch is what we use for a dilation. So a vertical stretch by a factor of a. A vertical stretch. So it's like if you took the graph by the top and the bottom and you just pulled it, okay, in both directions. The graph would get skinnier, it would stretch out. If the absolute value of a is less than 1, so if you have a fraction or decimal less than 1 but bigger than 0, so again, the sign doesn't matter, this is going to be a vertical compression by a factor of a. So what that means, by what the factor of a means, is you're basically multiplying all your y values by a. Now, vertical compression, imagine if you're on top and the bottom of a graph and you just smush it towards each other. Your graph's going to get fatter. It's going to be vertically compressed. So bigger than 1, you're going to have a skinnier graph. Less than 1, you're going to have a fatter graph, a wider graph. All right, and lastly, we already kind of know this. If your a value is negative, okay, in a parabola, in a quadratic, if your a value is negative, it opens down. Same thing for all of these. Instead of saying opening up or down, we say if your a value is negative, it reflects over the x-axis. So it reflects over the x-axis. Okay, so let's talk about some examples for these. Again, we're keeping it just generic functions, generic f of x. We're not doing any of the actual parent functions yet. So we got dilations and reflections depending on the a value, vertical translations depending on the k value, and horizontal translations depending on h. So describe the following f of x transformations. So we're going to say, what is happening to f of x if we do these things to it? All right, well, first up, number 1, you have, instead of f of x, you have f of x minus 5. So you have a minus 5 on the inside. Okay. Whenever there's something on the inside of the function with the x, it's a left or right. It's a horizontal movement. Okay. And minus 5, which we just wrote down, minus means you're going to shift to the right. So this means your whole graph is going to shift 5 units right. Number 2, you have a minus 7. Now the minus 7 is outside of the function. So you have f of x in the parentheses close, and then it's minus 7. Okay. So that's a k value. Okay, that minus 5 in the first one was a h value. This is a k value. K values go up or down. In this case, it's a minus 7. So this is going to shift 7 units down. Alright, so those are easy ones, just one of each. This third one has 3 transformations. Let's start with the plus 1 at the end. Okay. Plus 1 at the end means it's going to shift up 1 unit. Alright, and then you have an a value on this one. The a value is negative 2. Okay, the absolute value of the a value is just positive 2. Okay. The absolute value of the absolute value of a is bigger than 1, which means it's going to be a vertical stretch by a factor of 2. So all the y values that you would normally have, say you had a point like 2, 3, you'd multiply that y value by 2. And it'd be 2, 6. Alright, and then the last one is the minus sign. You have your a value is negative 2, which means it's less than 0. Which means your graph is going to reflect over the x-axis. Okay, now again, we can't say it opens down because not all of our parent functions had an opening. Some of them didn't open down, some went, both directions on y. So we say it reflects over the x-axis, unless we're specifically talking about a parabola. Alright, and this last one also has 3. The 1/3 out front is less than 1. So that means it's going to be a compression by a factor of 1/3. So your graph is going to be 1/3 of the original size, vertically. The +2 on the inside, +2 on the inside means left 2 units. And then finally the +6 on the outside means your graph is going to shift up 6 units. Right? So those are kind of all the different ways you could affect a function. Alright, let's do a specific function now. So now we're given a specific function. We're given f of x equals x squared minus, or plus 6. So this one is a quadratic. They won't all be, but this one is. Write the simplified transformed function. Okay. And I'm going to also describe what shift is happening. Alright, so f of x minus 10. We know that minus 10 is going to shift the graph down 10 units. But how does it affect the function? So we know how it affects the graph, but how does it affect the function? Well, we're just going to use substitution. We know what f of x is. F of x is x squared plus 6. So let's just use a substitution. Instead of writing f of x plus 10, we'll write x squared plus 6 minus 10. And then simplify that. All you have to do is combine like terms. 6 minus 10 is -4. So the transformed function is x squared minus 4. So what that means is if you took the graph of x squared plus 6 and you shifted it down 10 units, your new graph would be the graph of x squared minus 4. Okay, so that's what we're trying to find. We're trying to find the new transformed function. Same thing on the second one. Okay. We know multiplying by -1/3 on the outside is going to do two things. The negative sign is going to reflect it. It's going to reflect over the x-axis. And the 1/3 part, since it's a fraction, is going to be compressed by 1/3. But what does that mean in terms of our f of x? So in terms of our f of x, you're going to have the -1/3 out front. Then we're going to replace the f of x with what our f of x is. Our f of x is x squared plus 6. And then just simplify that function. So, do what your instinct says. It should say to distribute that 1/3. -1/3 times x squared is -1/3 x squared. And -1/3 times 6 is -2. So again, if you took x squared plus 6 and you reflected it over the x-axis and then compressed it by 1/3, that's the function. That's the new graph that you'd end up with. That's your new function. Alright, so both of those affected the outside of the function. What if we're affecting the inside of the function? So on this third one, you have f of x plus 5. Now this is actually a technique we've been doing all year, evaluating functions. F of x plus 5, if you have f of 2, you just plug in 2 for x. Well, we don't have f of 2, we have f of x plus 5. So f of x is x squared plus 6. F of x plus 5 is just going to be the same thing, but wherever we see x, we're going to replace it with x plus 5. Now that should look familiar. This is vertex form. Okay. Since we are dealing with a quadratic, our parent function was a quadratic, so this is vertex form. Now I want to simplify it out. I'm going to write it in standard form. So to write it in standard form, remember if you're converting from vertex to standard form, you expand, FOIL, simplify. So instead of x plus 5 squared, you got x plus 5 times x plus 5 plus 6. FOIL, it's going to be x squared plus 10x plus 25 plus 6. Don't forget the plus 6. And then combine like terms. Okay. So our final standard form is going to be x squared plus 10x combined to get plus 31. So again, if you take our original x squared plus 6 and you shifted it over 5 units to the left, we didn't mention that, but the plus 5 shifts it left 5 units. So if you took the original function and went left 5 units, this is the new function. That's the new one that we would have. Alright, these next two are kind of longer. Alright, this one has 2 transformations, and they're both translations. The minus 8 is going to move our graph right 8. And the plus 7 at the end is going to move up 7. So what happens if we transform, and again, I'll remember what f of x was. What happens if we transform f of x, which was x squared plus 6, what happens if we transform that and translate it right 8 units and up 7 units? What's our new graph? What's our new function? Alright, well, we're going to have to go through this. The minus 8 is on the inside. Okay. So the x minus 8 is going to have to replace x in the function. So the x minus 8 squared plus 6, because that's still part of the function. And then the plus 7 doesn't come into play until it's outside of the functions. It's past the function. So that plus 7 will go all the way at the end. Alright, now it's just simplifying this. Okay. Again, the minus 8 was inside the function. It was part of the function attached to the x value. Then you have to finish writing the function, and then finally at the end you do the plus 7 at the end. Alright, like I said, this is just a matter of expanding and combining like terms now. We're going to have to FOIL x minus 8 times x minus 8 plus 6 and then plus 7. If you FOIL those out, you end up with x squared minus 16x plus 64 plus 6 and then plus 7. Now again, since it's all addition and subtraction at this point, the parentheses don't matter, but I do want to keep it kind of piece by piece for right now. Combine like terms inside. It's going to give us x squared minus 16x. 64 plus 6 is plus 70. And then plus 7. And then in the very last step, you could finally combine the 70 plus 7. I'm going to move this other problem over. And you finally get your transformed function of x squared minus 16x plus 77. So that is the equation of the new graph if you took the original graph, which was x squared plus 6, and you shifted it right 8 units and up 7 units. This would be the new graph, or the new equation. Alright, and the last one, of course, is the longest. This one has all 4 possible transformations. So the negative sign out front is going to reflect it. We'll start on the inside. The plus 1 is going to move your graph left 1 unit. The 4 being multiplied is going to stretch the graph by 4. The negative sign out front is going to reflect over the x-axis. And then lastly, and we're going to talk about the order for these in a different part, the last one is minus 12 is going to shift your graph down 12 units. Alright, and just recall what the original function was. The original function was f of x equals x squared plus 6. Oh, plus 6. Alright, so let's write down what's happening. You have a -4 on the outside. It's being multiplied by the inside part of the function. But before I do that, I'm also going to mention that we have a -12. That -12 is also on the outside of the function. So that a value and the k values are always on the outside parts. The inside parts is always what you start with. You always start on the inside. The inside part is f of x plus 1. So you would take the original function, and wherever you see x, you would plug in that x plus 1. So instead of x squared plus 6, on the inside it's going to be x plus 1 squared plus 6. And now this is just, again, it's just math. We're just simplifying the expression here. Okay. We'll go piece by piece. Okay, I sped this up for you guys so you didn't have to watch 5 minutes of me doing math. Basically what I'm doing is I expanded it out. I'm going to FOIL here. Combine like terms with the 6. And then after that step, then you can finally distribute the -4. Now you distribute the -4 only to the trinomial, not to the -12. And then in the last step, you can combine with the -12. And that is the standard form version of that function. Now that's in standard form. There's GCF here you can pull out and other stuff. But we just want to write in standard form for now. Okay, so that's it. Check Google Classrooms for the homework. Have a great day.